So we left off example 3. We're just going to find the capacitance of this thing. We've got the area, we've got the distance apart. Just make sure you're in meters before you do all this stuff. And here we go. So it's just your charge per volt, but since we have all the physical characteristics, we're going to use the area of the thing per the distance. And there you go. You change it to meters, and don't forget about your little epsilon there, and shabam. Hey, it's an exciting 1.18 nanofarads of capacitance. Woo-ha! All right, so as far as shapes goes, normally we're going to talk about the parallel plates. Okay, but charge density on the surface is significantly affected by the curvature, hence the density of the charge is greatest where the curvature is the greatest. So we've noticed that when you guys are on the Van de Graaff generator and you'd point your fingers, you start hissing because you get a higher charge concentration at anything that's kind of a sharper edge. And it's easier to ionize the air when you have that higher density on that thing. So charges come off much more easily off of a point than they do off a big flat thing or a big round thing. Okay? So the electric field depends on how much charge you have near a spot. And if you get a high charge density, you can have a very strong field, a field great enough to ionize the air. So you're going to get some leakage off of the thing that occurs. So sometimes it glows a little purplish in your finger. Even in the old days of the ships going from the old world to the new world, sometimes you'd get a glow on the mast at night, a little purple glow at the tips, because the wind blowing across that sail would cause a potential difference in charging them, and in the charging of them, they'd get a point on the mast that starts to glow a little bit. I don't remember if that was called St. Elmo's fire or what. That might have been something different. I can't remember. So, dielectric strength. Alrighty, so this is how easy it is to break down the material. Okay, how easy it is to break, whether it's air or something else. Which why we have the leakage of charges off of things. So the electric intensity, it depends on the environment and the conditions, what the air is like. So it's high humidity, charges just zip right off of the stuff. It's harder to get a charge stored onto those things. But in general, to 1 sig fig anyway, it's about 3 million newtons per coulomb or volts per meter for spherical surfaces, and clear down to as low as 0.8 if you get a sharp point. So it's a lot easier to leak off a point than it is something round. All right, so let's talk about the materials that go in between your parallel plates. So you got your positive, you got your negative, you got your air. Well, the dielectric for this is just 1. You're just using the permittivity of free space. But as soon as you put something in between there, what happens to your dielectric, whatever you put on the inside, if this is positive, well, that's going to be attracted to the negative side. And of course, anything that's negative is going to be attracted to the positive side. And so what happens, that actually increases your capacitance. Because if this is negative right over here, and this is positive on this side, it's easier to store charges onto this thing. I can now put more electrons onto this side because since they attract each other right here, I can put more electrons on there and store more electrons per the same voltage, meaning with the same battery, I can get more charge to be stored onto there with the dielectric in the middle. Okay? So it does reduce the field, and the reason it reduces the field in between here, because now they're attracted to this side. So the field does get smaller, but what that does allow is it allows more charge to be stored on the thing by having a dielectric in between your two plates. So the separation of dielectric allows for more charge to be placed on the plates, hence you have a greater capacitance. All right, so advantage of these dielectrics. You got to get them closer together. Because it's going to be sometimes harder to break down the air, so you could get those things a lot closer together, which means you can have a very strong field in between there, and you store all kinds of charge between there. It also does increase the capacitance of the capacitor by putting it in there, and you can generally use higher voltages with that dielectric without it breaking down and zapping across and losing your charge by zapping from one plate to another straight across. And of course it can make the thing stronger. Okay. Alrighty. So insertion of a dielectric. Well, there's your dielectric, guys. You got a charge already there. You notice this is positive, and positive repels. So that's why it's doing that. And they've got the negative on the outside over here. what's going to happen to all this stuff as soon as you put a dielectric in between there? What's going to happen? Well, as soon as you insert a dielectric in between there seems to be like there's less charge separation. Well, remember, because now they're attracted to this, not so much repelling each other. So what happens by putting that dielectric in there, now they're attracted to this dielectric, and now they're not pushing on each other quite so hard. So now we're going to go through each of the steps of what happens if you have a capacitor that's already been charged, and this is just showing that it's charged, is all this do is like a meter, just showing that it's charged. As soon as you put that in there, well, we still roughly have the same amount of charge. This is like it's showing you the amount of it. We didn't really lose any charge, we didn't gain any charge by putting that in there, so the Q didn't change. So we're going to look at what happens to the capacitance, the voltage, and the field, and of course this is permittivity, that's not going to change as soon as you add that into there. So the first thing that happens is the field decreases, because remember, they're not attracting to the other side as hard anymore, they're attracting to this dielectric. And something that's surprising to a lot of people is the voltage actually decreases. You might ask, hey, why would the voltage decrease? They're not pushing on each other. Remember what potential is. Potential is how hard the charges are pushing on each other. It's electric pressure. As soon as you put a dielectric in between here, they're attracted to the dielectric, not so much repelling each other. So the actual potential, when you're not hooked up to a source, the potential actually drops on there. And your capacitance is going to increase because you can actually put more charge on there per volt. Since you have the same charge on there, the charge didn't leave, but the voltage actually did drop, you have a greater charge per volt, and your capacitance actually increases. So you could actually store more charge on there per volt than you could without the dielectric. So the permittivity increases, not of free space. The permittivity of free space didn't increase. The permittivity total increases because now it's not just air, it's something else. Okay, so dielectric constant material is the ratio of the capacitance of the material compared to in a vacuum. Okay, so that's how you'd find what the K is. What is it with the goo in the middle, without the goo? Okay, so if this is just without the goo, this is just a 1. So the dielectric constant for air or vacuum is simply just 1. Okay, so it can be given in terms of voltage, field, permittivity, and so on. So you could actually use what the voltage is without it versus with it, or you could use the field without it in there, with it on there, or the permittivity. It all works the same way as having the capacitance. The reason they flip with the sub-knots is because the inverse of each other. Okay, so the point is, it's just a ratio. That's how you found your K. It's a ratio of what one is with the other one. All right, permittivity of medium. The capacitance of a parallel plate with a dielectric can be found. Bang. So if you want to find the capacitance, it's not just the area. It's not just the distance between them. It's what do you have in the middle. If you don't have anything in the middle of the air, it's just your epsilon. But anything else you have in there is going to change the capacitance. Okay. So the permittivity of the medium, which relates to the density of the field lines. Alrighty. So there you go. So you can find what the new permittivity is, which is basically the new permittivity is the K times this thing right over there. And this is, of course, without it. Alrighty. So here we go now. Now we're going to find the capacitance and the charge stored. If we're using a 200-volt battery, that's a powerful one. Assume the dielectric constant is 5.0. Alrighty, so how in the world? Well, you have all your dimensions over here if you didn't notice. You have your 2 millimeters, you've got your area of a plate, and the only area that counts, what if one plate is bigger than the other? It's only the area of the smaller ones, the area they have in common, that counts. Okay, so we make them the same size. We don't make one larger than the other. So you're talking about the area of one side by itself, 0.5. Alrighty. So to find the new permittivity, you got to take your 8.85 times the 5 because that's the dielectric constant, and it's 44. And then you got your area on there, 0.5 divided by the distance, and bam, there's your capacitance. Why did they give you this information about the voltage? Well, that's what you're going to use to find the charge now. Now that you know the capacitance from the physical characteristics, you're going to find the charge stored if you're using it at 200 volts, and that's your capacitance. That would mean you'd be able to store a whopping 2.22 microcoulombs, or millionth of a coulomb of charge onto there. Okay, that means one of these has 2.22 microcoulombs of positive charge. The other represent a negative 2.2, or a lack of. So basically what the battery does is it takes off so many electrons off of one side and it puts it on the other. But that's the charge stored, or the electric charge you pull off one and put on the other. Okay, it's not the difference between the two charges, it's just how much charge you pulled off of one and put on the other is what this represents, 2.22 microcoulombs. Alrighty, so hey, another wonderful example. Find the field between the plates, and this, now we're looking for the field. Well, that tends to be a VED thing. Okay, but in this case, we're going to go back. You could use, excuse me, go back and use Gauss's law. We know the charge, we know the area of the thing, so that would be, and we know what the permittivity of it is. This is because you have the dielectric in there. So in this case, we could use that to find that the field is actually 100 newtons per coulomb in between there. Okay, that's one way to do that. The other way is your VED term. Usually that's the easy way to use, is just the VED thing. So since you have 200 volt, the same result is found in using the VED. You use your 200 divided by the distance, and bam, you get 100. Alrighty, so finally, capacitor. Has capacitance of 6 microfarads in the air with the dielectric. The battery charges the 400 volts and disconnected. What is the new voltage of if the sheet is inserted? What is the new capacitance? Okay. So now it's an air dielectric. You got a 400 volt difference between there, and the capacitor is 6 microfarads in the air. So first of all, what's going to happen to the capacitance when you add the 5 into there? It gets 5 times higher. Nice. It gets 5 times higher when you insert that into there. Okay. What's going to happen to the voltage when you insert that in? It gets lower. Very nice. It gets a lot low. It gets lower as you insert that thing into there. So first, we're finding what happens to the potential. Okay, so numerous ways to do this, but one way to do this is you could do it to 400 volts that you started with, and find out what happens. It goes down to the 80. Another way is you could have found the capacitance first, the new capacitance, and you have the same charge stored. Then you could have gone back and solved for the voltage. That would also work. There's a lot of different ways to do this. In this case, since it's 5 times 6, we talked about that, so that's going to be the 30. So once again, you could have done it this way, but sometimes I forget it. It's one way to do that. The other way is just to use your capacitance as your charge per volt. Your charge isn't changing, staying the same, so you just use that to find out what happens. Okay, so the capacitance increases, but the voltage decreases. All right. So if the 400 volt battery is reconnected after the insertion of the mica, what's the additional charge we place on the plates? So now it's going to go ramp back up to the 400. So it dropped to the 80. So you've already okay. So there you have a 400 volt battery inserted in the mica. So now how much additional charge will be stored on the thing? Well, originally it was 6 microfarads, and at 400 volts, that would be the amount of charge stored on the thing. Okay, but now if you increase it to a 30 at 400, that's the amount of charge that was stored. So if you want to find the additional charge added, it's just the difference. Okay, and it's so by having on the inside, we've added a lot more charge to the thing. In fact, it's going to be 5 times the amount of charge because it has a dielectric constant of 5. And so there it is, millicoulombs. All right, finally the energy. We're going to stop at the energy thing right here because we're at 14 minutes and I only have 1 minute, so we're going to take another video to talk about how much energy is stored onto this. All right, see you in a few.